So let us start today, Vishnu.
Yes, please go ahead when you're ready.
Okay, thank you. So the first talk is by Babak Haghighat from Tsinghua University Machine Learning, the Kitaev honeycomb model. So Babak, please go ahead. Thanks.
Yes, thank you very much for the invitation, and it's a pleasure to give a talk at this string data conference. And I hope I can connect to the string side also properly, because the talk is about the Kitaev honeycomb model, which traditionally belongs to the condensed matter part of theory, but I think it has implications for all directions. So that's why I think it is fitting. So so the work is about machine learning, the Kitaev honeycomb model, and it is a joint work with Mohammad Reza Nurmandipur and Yoran Sun, and it appeared February this year on the archive. And let me begin. So first I want to come to an introduction of the subject, and I want to give you a historical account. So all these models have actually to do with topological phases of matter, and the most famous one is, of course, the fractional quantum Hall effect, and the one which is actually related to the phase which is related to the phase I will be interested in is the one with filling fraction mu is equal to 5/2, and that one was observed experimentally already some time ago by a measurement of the electric Hall conductivity by these people which you see here, and some of them got the Nobel Prize. And somebody says that we are only seeing the title slide. Is that true?
Yeah, your slides are not advanced.
Yes, that's true.
But I did share the screen. Wait, one second. What do you see now? You see the title slide, and now?
Yes.
You see something else?
Yes, we see the second slide.
And now?
Non-abelian phases of matter.
Okay, let me go to full screen and see whether it still works. Does it still work?
No, we can only see non-abelian phases of matter.
Yeah, that's good. But now, how about now? It goes to the next page or not?
No, it's not advancing. Full screen is not working.
I see. That I don't know why. Maybe I just make it very large then. Let's see how I can do that. Okay. So this is full. So
it works if you share the entire screen and then go into full screen on your presentation.
Now nothing. Now it's not working.
Now it's fine. Now it looks fine.
So I'm going back and forth. You can see that?
Yes.
Okay. Then let me just go here, and I think it should be fine. Yeah.
Okay.
It's, I think, not full screen, but almost full screen. So good. So this is the theoretical explanation was given in terms of a non-abelian phase of matter, and it was in the seminal paper by Greg Moore and Nicholas Reed. And so here they explained this fractional filling fraction 5/2 by a non-abelian phase, but there were also at the same time other explanations in terms of abelian phases. So this matter was not completely settled until actually a final experiment had been done, namely the measurement of the thermal Hall conductivity, which was a very recent result from 2018. And that one finally confirmed that this is indeed a non-abelian phase of matter. And this is the first experimental confirmation of non-abelian phases in nature. And so it's an exciting time to actually study other models with these kinds of properties because they seem to exist indeed. And one a theoretical model, which has not yet been realized experimentally, but may be very promising, is the Kitaev honeycomb model proposed by Kitaev in 2006. And this provides a spin lattice realization of non-obedient phases. So let's look into that. So this is an introduction now about the Kitaev honeycomb model. So I want to say a few words about that before I go to the actual machine learning realization. So yeah, the Kitaev model is a spin lattice model on a honeycomb lattice. So you have this honeycomb lattice, as you can see, and you have on each side or vertex, you have a spinner, and it has spin 1/2 particle, spin up, or it can have two states, spin up or spin down, let's say in the z direction. And now the Hamiltonian, so what we are interested in is to put this whole thing on a torus. So we give it periodic boundary conditions. And so you can see that you go a certain direction along the complex structure tau, and then it becomes periodic, and you go also along the other direction and it becomes periodic. And the Hamiltonian of this system now is given by these pairwise interactions of these Pauli matrices. And it's very special because it distinguishes which type of interaction you have by the link, which is between two sites. So if you have a z-link, which is a vertical line, then you have interactions in terms of Pauli z matrices between these two spinners. And if you have an x-link, you have Pauli x interactions, and along y links, there are Pauli y interactions. So these are the sigma xi, sigma xj, and sigma yi, sigma yj, and so on. And you can also turn on a magnetic field. So, so basically you turn on the magnetic field, and there is a splitting of energy through some Zeeman effect. And you can do perturbation theory for small magnetic fields. And what you see is this, what emerges at first order in perturbation theory is this triple interaction of these three Pauli matrices at each vertex. So this one talks to the spinners connected to that vertex through these three links attached to it. And K is, as I said, proportional to this magnetic field and other constants. So that's the model. Let's go now to the specifics of it and how Kitaev solved it. And here, by solution, I mean that Kitaev managed to actually write down the full energy spectrum of this model for all excited states, the ground state, and so on and so forth. There are several ground states, though, because we are on torus, and that's actually a very important property of this model. So let's come to Kitaev's solution. What he did is to realize each spin 1/2 particle by complex spinless fermionic modes. For each spin 1/2 particle, he introduces two complex fermionic modes, A1 and A2. And if they are both, let's say, filled, then that means that you have spin down. And if it's empty, you have spin up. And of course, you have these intermediate stages where you have just one fermionic mode, and those do not correspond to anything. So those have to be projected out. So that's the way it is engineered. So you basically have a too large Hilbert space, but then you project to the physical subspace, which is given by this operator di at each site. And this operator di projects exactly to those states with eigenvalue 1 to those states which have either two complex fermionic modes or none. Now, in order to act on this physical space now with Pauli matrices, we have to somehow model these Pauli matrices through these fermions as well. And that can be done. What one does is first to define certain Majorana modes. So these are real fermionic modes or imaginary modes. These are the Ci and Dix, and Diy and Diz, which are these combinations of these complex fermionic modes such that C, B, and the BXY, Z, they are real. So they are Majorana fermions. And then you can realize Pauli matrices in this way. So you basically have I times BI alpha times CI, and this gives you the Pauli matrix sigma I alpha acting on site I. So this is always faithful once you project to physical states, and these Pauli matrices, as defined through these Majorana fermions, will satisfy the right computation relations and so on and so forth. So that's very neat and nice. And then you can ask, okay, so how does the Hamiltonian look like? And the Hamiltonian will have now consists of these products of these Pauli matrices. So what you get is for these sigma I alpha, sigma j alpha, you get Uij hat Ci Cj, where these Uij hats, these are given in terms of the products of the Dij's, and the triple product is the one given here. So this can be also written in terms of the terms of two U operators, and then this projection operator dk, and then Ci and Cj. So everything is now expressed in terms of these Majorana modes. And what you can do is to look at the properties of these U hat operators, and it turns out that they are antisymmetric in the Ij indices, but otherwise they square to the identity and are Hermitian. So what you can do, you can write now the Hamiltonian in terms of these Hermitian operators, and you get this H is equal to sum over Ij, A hat Ij, Ci Cj. And this A hat is antisymmetric. And the first thing one can note is that this Hamiltonian commutes with the projection operator, which is nice. So we can diagonalize the Hamiltonian, and is compatible to restricting to the physical subspace. But there is more to the story, namely we have other observables which commute with the Hamiltonian. These are plaquette operators. So if you take the product of Pauli matrices along each of these honeycomb plaquettes, then that is actually, that one commutes with the Hamiltonian. And that can be expressed in terms of the Uij hats. And these plaquette operators, they have eigenvalues plus minus 1. And they also commute with the Hamiltonian and these projection operators. So that's all good. But the Uij's actually do not commute with the projection operator. So the physical subspace, if you restrict to that operator will actually change the eigenvalue of Uij because it anti-commutes with it. So what you can think of how you can think of this Uij as gauge degrees of freedom, because their actual value is Z2, but the physical observables or gauge invariant observables are these plaquette operators. These you can think of them as Wilson lines of the Z2 gauge field, and those are better. Those better commute with the projection operator, but the Uij's do not. So they are kind of arbitrary, but the product has to be kept fixed in each sector. So the way this then works is that by tuning these Uij eigenvalues and the plaquette eigenvalues, you get vortices. So here is an example. So you have the upper left plaquette has a plaquette eigenvalue -1, and that can be achieved by taking one of the Uij's to have a minus eigenvalue. And then you see that the other ones are plus because the products of the Uij's is 1, and there is another plaquette with eigenvalue minus, and so you have these kinds of vortex configurations, and you basically you can generate them by string-like operators, and these string-like operators are given by this O1 hat and O2 hat. They generate vortex pairs in vertical or horizontal directions, and you act with those guys, multiple of these operators in different combinations. You can get different strings connecting vortex pairs. So that's good so far. But now let's see how to compute actually the energies, because that's part of the solution, to compute the energies of this system. And the ground state is, of course, the lowest energy eigenstate of the Hamiltonian. And by a theorem of Lieb, that state resides in the no vortex center. So all plaquette eigenvalues are +1. And here the Hamiltonian can be diagonalized in momentum space. So you do Fourier transformation, and then you go to momentum space. So modes are not anymore labeled by lattice sites, but by momenta on this lattice. And you can express them in terms of these fermionic modes gamma k labeled by momentum k. This k is discrete. And yeah, so that's what you get. These are just fermionic creation annihilation operators. And these energies, they are given in terms of the square root of epsilon k square plus delta k square. It all depends on these momenta, and the momenta are discrete, and they take values in the first Brillouin zone of this lattice, which is depicted there. So you can compute this ground state energy by taking the eigenvalues of the gamma k dagger gamma k to be 0. So those fermionic modes are not filled. And what you get is this is the ground state energy, -1/2 sum over k ek. And if you then act with these gamma k daggers, you basically create excitations of the system. So these are certain fermions running with certain momenta there, and these are called quasi-particles. And they will generate a higher energy, these quasi-particles. Now, it turns out that you have now two things. You have these vortices, you have these quasi-particles, and it turns out that these vortices all bind a Majorana zero mode. And when you fuse two vortices, you can actually create either a quasi-particle, these two Majorana zero modes, they form a complex fermion and make a quasi-particle or not. So this is, you can end in two different states when you fuse two of these vortices back together. And this situation is actually kind of similar to Ising anyons, because this is what Kitaev observed. Because the Ising model, you have these whatever language you talk about it. Let's talk in CFT language. You have this Ising primary fields, and then there is the spin operator, which has exactly this property. So what one does is one associates the vortex of the Kitaev model to this sigma primary field of the Ising model. The ground state is the vacuum operator, and this quasi-particle excitation that can be actually identified with a fermion, with a psi in the Ising model. And all these fusion rules work out perfectly, because if you fuse two vortices, as said before, you can end up with a quasi-particle or none, and that is reminiscent of the fact that sigma times sigma is either vacuum or psi. Yeah, okay. Let me then come to the solution of the model. So the solution of the model is in terms of a restricted Boltzmann machine. And because so far the solution was only for the eigenvalues, not the wave functions. We want to find the wave functions to be able to do more stuff. And the Hilbert space is 2 to the n dimensional, where n is the number of sites, so it grows exponential with n. So that's a kind of hard if you want to diagonalize such a huge Hamiltonian. But we make an ansatz in terms of a restricted Boltzmann machine, where the parameters of this ansatz only grow polynomially with the size. So you have this spin basis states S, and then you have this phi omega, which is a given in terms of this Boltzmann machine, which is, so these weights phi are determined by this neural network, which you see here. It consists of a set of visible layers. These are the spins, either up or down, and hidden layers. And there are connection weights between them. And this basically tuning these connection parameters tunes for you the phase, the superposition phase for each spin configuration. And you have to sum over all these hidden modes. If you do that, the hidden modes also take values 0 or 1. And if you sum over those, you get this particular expression in terms of the cosine hyperbolicus. And you have these weights of this neural network. And this way you can model the wave function, which is basically which what you want to train such that you get an eigenstate of the Hamiltonian. And you can train it by actually doing energy minimization by computing the expectation value of the Hamiltonian and do stochastic gradient descent. And at each step then tuning the parameters of the neural network, the weights, such that you ultimately reach the minimal energy. In our particular case, we find that we also have to do a projection onto translation invariant states after each training step, because this is required by the physics. We are living on the torus, and everything is translation invariant. So we also employ such a projection. Now let's come to the data. So here the table shows all the data. The first 3 entries, actually 4 entries of the table, shows all the results which can be done analytically or through brute force diagonalization. So these are all exact results. And maybe you should look only at label C, D, and E. C is exact diagonalization of the Hamiltonian. So this is definitely exact, done by the computer. D is using an RBM or neural network of the so-called netcat package. And E is the result which we do after. So we wrote that, we used first the netcat package to do that, but then we found that it's not suitable. So we wrote our own PyTorch package which can do that. And as you can see, the values in the row E match very well with the ones in the row C, which are the exact ones. And we also can turn on non-trivial magnetic field, and that also matches. So that's all good. And moreover, we can also create these string operators or vortex pairs just by acting on the learned neural network. So we don't have to train it again. We just tune the parameters, or we just make an adjustment on the parameters after the state is learned, and we can create vortices. So that's actually very neat and nice. Now, in the remaining time, actually, I want to go to something which is a bit more connected maybe to string theory or conformal field theory, because as I said at the beginning, this Kitaev model is related to Ising anyons, or to the Ising model. Namely, the bulk of the model is a 2 + 1 dimensional theory, but the bulk is gapped, but the boundary modes are actually gapless and chiral, and it is believed that it is indeed flowing to a chiral sector of a CFD. So what we want to do is we want to model the wave function using a conformal block. And that's what's described here. So we use an ansatz for an SUPK WZW conformal block. And the ansatz is basically shown on the bottom of the page in terms of the so-called Pfaffian state. And this IJ here is basically a spin singlet. It is because we are using
5 minutes.
Okay, good. We are using the spin singlet of the WZW model, the spinor field of the WZW SU2 level 2 model, because that's the one we are interested in for this, which has fusion rules of the Ising model. And but this one has actually too many degrees of freedom. It has a spin 1 field, but we want spin 1/2 fields to model the spinors at each side. So you see this ZI and ZJ, these are the points on the lattice where these spinors are situated. And we want to basically insert CFD operators at these points and then project down to a spin 1/2 state, similar to what Kitaev did. And that turns out to be possible. So one can project down from the spin 1 singlets to spin 1/2 states, which are actually eigenstates of the permutation operator of sigma x, sigma y, and sigma z. So that's actually, there is a nice projection to those types of spinor pairs, which are eigenstates of the permutation operator of these Pauli matrices. And this will play actually a very important role in a minute. But first, let me say one more thing. The whole thing has to be uplifted to the torus because we are on a torus. So we have to replace everything by theta function. And the correct way to do this is to actually write a Pfaffian of ratios of theta functions. And what you see is that now you have actually 3 spin structures for these theta functions, 3 even spin structures, and this nicely corresponds to the fact that the ground state is triple degenerate. So we have 3 wave functions here in terms of these theta alpha zi minus zj times this spin singlet, which we project down to spin 1/2 states, and so on and so forth. And you see that this is all translationally invariant, because we have these theta functions, and all the phase factors cancel out nicely, and it's translationally invariant, but it has another invariance, namely modular invariance, which is actually very useful, because if you look at the Kitaev Hamiltonian, it has a very nice symmetry. It is symmetric under permutation of the Pauli matrices, and at the same time, exchange of the links, Z-link with Y-link, Y-link with X-link, and so on. So these are 120-degree rotations, isotropic 120-degree rotations on the lattice. And if you do these two operations simultaneously, the Hamiltonian is invariant. So the ground states, so this operation commutes with the Hamiltonian, so it should at most permute the ground states of the system. And this turns out to be, in fact, the case, because this 120-degree rotation on the lattice, this is nothing else than a modular transformation, because this multiplies the difference zi minus zj by tau minus 1. And looking at the honeycomb lattice, tau is fixed to a very particular complex structure given by the honeycomb structure, such that actually, if you have the theta function of tau minus 1 times zi minus zj, this is proportional to the theta function without that tau minus 1 times this thing. So without the unrotated guy, and up to some phase factors. And but then in the conformal block, these theta functions appear as ratios. So these phase factors cancel miraculously. So, but the spin structures are rotated. So that means that doing this performing this operator, these ground states are rotated. So we have 3 ground states, and they are being rotated among each other as we act with this operator. This is exactly as it should be, and that's actually what I want to point out, namely that this is would be made. So we have modeled the ground state. This is a conjecture; it's not completely proven yet, but it has all the symmetries. And we have modeled the ground state using conformal blocks. On the other hand, we have learned the ground state using the neural network. So this poses the question whether we can basically learn quantum field theory correlation functions, in this case, conformal field theory correlation functions, using neural networks. So that is the main point of this part. And now let me just come to the conclusions. So we have seen that the honeycomb model is a spin lattice model, admitting topological order. It has a sector where we have a non-abelian anions with non-abelian braining statistics. We have been able to solve or construct the eigenfunctions of the Hamiltonian using a restricted Boltzmann machine. And we have found the lowest energy eigenstates using stochastic gradient descent. And we can build excited states using vortex pairs. And we can identify ground states conjecturally with certain tests passed with conformal blocks of certain CFTs, and show that the ansatz has the right symmetries using modularity. So that's actually exciting, because maybe, as said, we can use these neural networks to learn something about conformal field theory correlation functions, or the other way around. So this might put the whole thing into a more general context. So yeah, that's it. Thank you very much. I hope I'm still in time. Yeah.
Thanks, Babak, for the talk. Is there any question? We have a few minutes for the questions.
Yeah, Jim?
Hi, Babak. Good to see you. Just a quick question. I was wondering if you could comment a little bit more on how it was that you created the excited states given the trained network for the ground state, and sort of why it works. Is it just that you have some localized finite energy gap or something like that?
Yes, so the way it works is that we have excited states. We cannot create all excited states. What I'm talking about is we are going from the no vortex sector to vortex sectors, where we have vortex pairs.
Yep.
And this can be, of course, done by applying these string operators along alpha links, as you can see on this page on the top. And if you take this thing operator, act with that guy on the neural network state, you will see that this is actually equivalent to shifting the neural network, the parameters in this particular way. You adjust the learned parameters in this particular way. So this is the same as acting with that operator. And here we have done an example, but this is actually a too small lattice. One should do it on a bigger lattice. You see in the ground state has almost all placket eigenvalues 1. Then we can create a vortex between placket B, vortex paired placket B and placket D. And then we move it around such that it is gone again and everything is back to almost 1. But here you see the energy is actually higher than the first one after annihilation. And that's because these are actually not the pure ones. These are highly entangled states. So you will arrive at the no vortex sector, but you will have maybe quasi-particle excitations here.
I see, but you can arrive in the non-trivial vortex sector as well. And,
Yeah, you arrive at the non-trivial vortex sector, yeah.
and it's via consideration of the direct action of how these spin operators would act and induce a vortex.
Exactly, on the neural network parameters, yeah.
But I guess a priori, you wouldn't have necessarily expected that action would sort of be faithful with respect to representing the right sort of state or something like that.
Yes, that's true. So that's why we do get a excited vortex sector, but only up to quasi-particle excitations, which do not change the vortex sector. So it's not the ground state of that vortex sector, you see?
Yes.
It's an excited state.
Right. In some sense, the thing that protects you is the topology. You move into a different topological sector, but it may be an excited state. I got it. Thank you.
Exactly. Sven, you have also a question?
Yeah, hi Babak.
Hi.
So this is just on the conceptual side. So how much guarantee have you got that RBMs are actually giving you the right physical solution? Because they're known to kind of not being the best thing for, say, if you apply them in an Ising model normally.
Well, in this case, we are just comparing the energies, and as you can see, the energies are all matching very, very precisely. But we are actually doing more. We are comparing also certain symmetries of these. So we checked the Hamiltonian has certain symmetries, and we checked the symmetry, some of the symmetries, once we have the learned state that it indeed obeys those symmetries.
And so the continuation of that question is kind of what have people done in terms of looking at it with like tensor network approaches, etc., on these systems?
Sure, the tensor network approach also can be done, but that one has way more parameters, as far as I understand. So it is even harder. It's harder to realize that or to train that and so on practically. Whereas this one has only a polynomial number of parameters. That's not the case for the tensor networks.
Yeah. So it's just have people done this because it's like an long.
Yes, for this particular Kitaev model, people did look at tensor networks just recently also. Yeah, they have some nice results there as well. Using tensor networks, in fact. So that's another group. We cite them in our paper. Yeah.
Is there any other questions? No. In that case, may I ask one question? So, in this model, the RBM you're using, is it a fully connected RBM? Or you are using any kind of...
It is fully connected, but only one layer, right?
Yeah, that's
but
fine.
It's fully connected.
Yeah, but additionally, what is the correlation length of this model at least in the
These are very interesting. These are very interesting questions. These things. So we find that indeed these nodes can talk to very far away nodes. So it is very highly entangled, the state we find, but we didn't do any further tests or computing the entropy or anything like that. That would be actually interesting to do for these states to see what the correlation length and so on is. But it is very non-trivial. It's not only talking to the neighbors. So, like some other models. For the toric code, I know there is a solution where you only talk to the neighbors, but that's not the case here.
I see. So another related question is that did you look at any higher correlation or only at the energy?
We only looked at the energy, but we could easily also compute higher correlations. Once the wave function is learned, that's not a big deal.
But do they match higher correlations?
So we did not look at that. We did not look at that.
Okay.
That's something we could have done, but we were more interested in this conformal field theory business. So we were trying to model the ground states in that way. But that's definitely something to do. Yeah.
Okay. If there are no more questions, then let us thank Babak for this wonderful talk, and let us go. And let us go to the next talk. I think the next speaker is Kostis Papagourikakis. So, Kostis.
Babak has to unshare for me to share my screen first.
Yeah, 1 second.
Sure.
I'm trying to unshare that. Okay. So